Yeah, this one. Yeah, well, like it's better than nothing. So how you do it is basically, as I explained there as well, you have iterations. Okay, so you start with some sort of iteration, typically with a while loop, because it has to satisfy something before the iteration stops. For loop is when you really know the boundaries of when it's going to be stopping. Now, it doesn't mean that you can't do it with a for loop, but while loop is typically a bit more efficient for those types of looping that you don't know when it's going to be stopping, right? So you start there. What you have here is your x of scan and your x of BIM, right? X means the XYZ coordinates, okay? In the previous basically slide, I showed that if you have a BIM element, you can actually decompose it into points, right? Using Cloud Compare, but we're going to be talking, and I'm guessing you guys went through the lectures as well. Those ones actually give you the STL and then the projection, and then we use that as the X of BIM, okay? So at the end, we still have some XYZ there that we're going to be using. What we do is we basically find the closest point that are less than a threshold. We talked about this threshold as well. This threshold has to be a function of both the course registration parameters and the point standard deviation and covariance, right? So both of these need to play into this. Here, for you, the sake of you guys' sanity, we're going to basically put a number, let's say 2 centimeters, 3 centimeters. For your project, I would like you guys to actually figure out which one would provide you a better results. We start with some sort of threshold. Then when we find these, and we talked about how you can use the KNN search algorithm for this so that we can find the closest point between them. It will give you the identity of it, the distance, all these types of things. From that, you then go, you have a set of points that are target and source. Then you do a rigid body transformation for that, and you get the rotation and translation. Okay. Once you have that, which is basically this, which you want to take the scan into the BIM. That's what the idea of scan versus BIM is. Then you want to estimate the root mean squared error for this translation, which is which is basically you getting this right-hand side and subtracting it from the left-hand side, and then basically getting the norm of that. So it's X, Y, and Z there. That is basically whatever that scan that is rotated, where that lands. And then you want to subtract it from the other one and get the actual L2 norm of that for each and every one of them. And then what do? You basically go and get the average, and then you get the square root of that. If the root mean squared error between 2 consecutive iterations is actually smaller than a particular threshold, then what you do is you say that this is good enough and come out. Else, you basically now do a new scan with basically from the previous one. So whatever this X scan times R times plus T provided, that's going to be your new set of points. You then are going to be projecting it onto these planes, and then you basically are going to be doing it over and over again. If you have the X of BIM, originally, basically from let's say Cloud Compare with a density, you don't need to recalculate the X of BIM. In our case, we will. What we do is we get every point projected onto it, see if it's within the boundaries. If it is, then we're basically going to be putting that as the corresponding point from the X of scan to the X of BIM. The next time that you're going to do this iteration, your X of scan is this, but you also have to recalculate the X of BIM. And of course, your iteration number goes next. Why this is good? Because if you have an iteration cancellation here, you can basically put it there and keep it there. Okay. So if you want to do it in MATLAB, you want to decompose it, this, and then perform the ICP. That's the whole idea. Every point onto every plane, find if it's in the boundary or not, if it's in the distance threshold or not. If it is, it's going to be the point corresponding to this. From that, do basically a rigid body transformation. If the rigid body transformation works, then you go to the next one. Okay. So for this, what you need is some basic ideas of basically a plane, which is represented by a point and a normal, your origin, and the projection distance. So the plane parameter, which is the attributes that we did for the previous ones as well, is represented by A, B, and C, which is your normal vector directions, basically representing the x direction of the normal vector, y and z. And then this is basically going to be your intercept. So this is this, this is this. Basically, whatever points you have times the normal vector is going to, on the plane, is going to be giving you the d value, right? So then what needs to happen is that whatever point x that you have, that is your point cloud, you know, that you want to see what the projection is from that particular plane. What you need to do is you need to now project it back to that plane. The formula for the projection is basically you have your x, you have to dot product it with your n minus d. This would give you the distance. Or if you want to do it in a simple form, which is what I've done in basically what we've going through with the lectures and everything, is that whatever this attribute is, which is A, B, C, and D, now instead of D, I just put a 1 here, right? This just makes it as a matrix multiplication between this A, B, C, and D and this. That's it. Now, because your X is going to be rho, you're going to probably have a transpose of this, right? And then the basically the eta on the other side of this, but I'll let you guys basically figure the MATLAB computation there for yourself. And what this provides you is the x of p, which is going to be that projection, which is essentially whatever your x is in the direction of the normal vector minus dx times, right? This would give you the projection. That's it. So simple formulation, providing you with the x of p, which is the projection onto that plane. Okay, so let's do the ICP formulation for the plane model situation. So this time, again, we do that and we find the closest plane in the BIM to each point of the scan that is smaller than this. Then project the point onto the plane. So you then go, let's say it's this point here, you project it inside. This is going to be the projection of that, right? Project the point onto the plane and check if it's within the boundaries of the plane. That check within the boundaries is very important. If it's not, then this point is not going to be there. If it is, then you basically are going to be projecting it there. We start by every plane because if there is going to be this point might not belong to this plane, but might belong to another plane, okay? So we do it for every plane first because we want to get the one-to-one relationship between the points and the plane, not the other way around. So we're not going for every point and seeing which one is the best. Then once you have this, so for every plane, you have an X of BIM that has an ID with an X of scan. Here, you do the rigid body transformation. From that, you get the root mean squared error. If the consecutive iterations is less than a threshold, you basically do that. If not, you go to the next one, perform the exact same. So the X of BIM is not something that is going to be the same. It's going to change every time.